And here we are, ready to do some sample kinetics problems. This is from chapter 12. And so we're going to look at some different examples of equations using kinetics, calculating rates, looking at rate laws and rate constants. And so I'm going to do a couple examples in this video. And then the next video will have additional examples. And so they're going to get a little more involved with each step. We're going to start and say we have a chemical reaction here, and we're asked to find the average rate. And so we're given an image, and we see that at time 0, when we're starting this reaction, we have 1 mole of compound A and no moles of compound B. So A are the little red spheres, compound B are the blue spheres. So you can see over time, we're increasing the amount of B that's present in the chamber, and we're decreasing the amount of A that's in the chamber. And so what it's asking for is, what is the rate at which A disappears from 20 seconds to 40 seconds? So we're looking at this process here, from this amount of A to this amount of A. So what would be the average rate at which A disappears, right? And so we can say that the rate is equal to negative change in the concentration of A over the change in time. And we say negative because A is going away, right? So A is disappearing. And so when we look at the change in concentration, it's going to be the final concentration minus the initial. So I have negative, and then my concentration change, 0.30 molar, minus 0.54 molar, and then divided by my change in time. Well, my change in time was 40 seconds. My initial time was 20 seconds. So I have my change in concentration over my change in time. And so I end up with a rate of 1.2 times 10 to the negative 2 molar per second, right? So the 0.3 minus 0.54 is going to give me a negative number. And so the negative out front makes that a positive rate. So the A is disappearing, which gives me a negative concentration range, but I end up with a positive rate. And so 1.2 times 10 to the negative 2 molar per second. All right, so that would be the average rate of that reaction over the second 20 seconds of that reaction. All right? Okay, let's look at our second example. Right, and in our second example, we're going to use the graph, and we're going to calculate the instantaneous rate of the disappearance of C4H9Cl, right? And so when we look at this graph and we say, okay, what's our instantaneous rate? So at time equals 0, right, we can see we get an instantaneous rate, and that over time, right, that starts to change a little bit. And so the instantaneous rate at t equals 600 seconds is going to be different than the instantaneous rate at t equal to 0 seconds. So what we have to do to figure out this rate is we have to figure out what the slope of the curve at t equal to 0 is. And so the way we do that is we draw a tangent line here, tangent to that line at t equals 0, and that becomes then the hypotenuse of our triangle, right? And so you can see this golden shaded area is our triangle, and if you can see this dashed green line here, that represents the tangent line to this graph at t equals 0. And so what we can do now is we can calculate the slope of that line, right? And that slope of the line is going to help us figure out what that change in concentration is, or at least help us figure out what our rate of our reaction is as far as the rate of the appearance. And so when we look at this hypotenuse line, right, this hypotenuse line, we have, again, we're going to be looking at the rate, and our rate is equal to minus the change in C4H9Cl divided by our change in time, right? And so we can say that if we look at our final concentration minus our initial, right, for this golden triangle here, it's 0.06 molar minus 0.100 molar, right? That's our change in concentration. And so our change in time, well, we can say that that goes, and we can say that that's a 210 seconds. So 210 minus 0 seconds, right? That's our final time minus our initial time. So we get our delta concentration of 0.04 divided by 210. So we get a 1.9 times 10 to the negative 4 molar per second, right? And so that would be the instantaneous rate of that reaction, right? So when that reaction first starts, right, we draw our tangent line and we figure out what that is. And so that's our instantaneous rate of our reaction. All right. So now we're going to look at relative rates, and we're going to look at the relative rates of the appearance of ozone and the relative rate, or the relative rate of the disappearance of ozone, and the relative rate of the appearance of oxygen. Okay. And so we say, if we look at the stoichiometry of this reaction, right, we can see that for every 2 ozones that are being consumed, we're producing 3 oxygens. So when we write out the relative rates, right, so for part A, we would say the rate is equal to 1 over 2, because that's the coefficient in front of the ozone, minus, and this is multiplied by the change in concentration of ozone over the change in time, right? So that would give us the rate of the ozone, change in concentration over change in time, 1 over the coefficient. That's going to be equal to minus 1/3, right? Because we have a 3 in front of the oxygen, minus 1/3 times the change in concentration of oxygen over the change in time. Right, so that's our relative rates, right? How is the rate at which ozone disappears related to the rate at which oxygen appears, right? So the rate is equal to 1/2 the disappearance of ozone, which is equal to 1/3 the rate of appearance of oxygen. Right, so now we say, if the rate at which oxygen appears is equal to 6.0 times 10 to the negative 5th, at what rate is ozone disappearing at that same time? So we're given the rate of oxygen and asked to figure out the rate of ozone, right? So we want to get the rate of ozone over here by itself, right? So minus the change in the concentration of ozone over delta T, right? Well, to get this by itself, if I multiply both sides by 2, then I get 2/3 times the change in concentration of oxygen over the change in time. And so we were given this value here, delta O2 over delta T, that equals 6.0 times 10 to the negative 5th. So my disappearance of ozone is equal to 2/3 times 6.0 times 10 to the negative 5th molar per second. So I get 4.0 times 10 to the negative 5th molar per second. Right? So that is the rate at which my ozone is disappearing. Right? So then that value is 2/3 of that rate. So if I take half of the ozone rate, that's going to be equal to 1/3 of the oxygen rate. So half of ozone would be 2 times 10 to the negative 5th, and 1/3 of the oxygen would also be 2 times 10 to the negative 5th, right? So that coincides with what we figured out for part A as well, with the relative rates. Okay. Let's look now at relating the rate law to the effective concentration, right? How is all that now put together? Rate law, concentrations, right? So this reaction tells us we've got A going to form B and C, okay? So my A's are red, and my blues or my purples are B. Okay. And so in these different reactions, I've got certain amounts of A and certain amounts of B. And so depending on how much A and B I start with, how is that going to affect the overall rate of the reaction? And so which one of these, right, is going to increase or have the fastest rate? So my rate is equal to K times the concentration of A times the concentration of B squared, right? And so for box 1, right, I have 5 reds and 5 purples. So my rate is going to be equal to K times my 5 reds times my 5 purples, and my 5 purples are squared, so that would give me 125 times the rate constant. So my rate is going to be 125 times the rate constant. For my second box, in my second box, I have 7 reds and 3 purples. So there, my rate is going to be equal to K times my 7 reds times my 3 purples squared, right? So that gives me a rate equal to 63 times my rate constant, right? So you can see that one's a little slower than the first one because this is the same rate constant, so that K isn't going to change, right? So this is 125 times that value. This is 63 times that value. And then my third box, right? In this third box, I've got 3 reds and I have 7 purples. So my rate is going to be equal to K times my 3 reds, my 7 purples, and my 7 purples are squared, so that gives me 147 times my rate constant. All right, so now if I want to rank these from the fastest to the slowest, or we want to rank them in order of increasing rate, right, then we're going to say that, right, 2 is slower than box 1, which is slower than box 3. So box 3 would be our fastest. 2 would be our slowest, right? So we've got 2, 1, and then 3 if we're ranking those in rate, in order of increasing rate. Okay. Let's look at reaction orders and rate constants, right? What are the units for rate constant, right? So this is a question that is asked frequently. And ultimately, the units for the rate constant do depend on the reaction order. So when we have a rate or we have a reaction, and so in this reaction, we've got the first reaction is 2N2O5 as a gas, decomposing to form 4 NO2s as a gas and oxygen as a gas. And the rate of that reaction is equal to the rate constant times the concentration of N2O5, right? Well, in that case, right, in this reaction, right, so in A1, it's N2O5 to the first power, right? And so the exponent on that is a 1, so that means that reaction is first order, okay? Just simply, what is the exponent on that? Which means that if I double the concentration of N2O5, I'm going to double the rate of my reaction. That would be a first order reaction. If I look at the second one, right, A2, here I've got CHCl3 as a gas, adding chlorine as a gas, and I'm getting carbon tetrachloride as a gas, and hydrochloric acid as a gas, or hydrogen chloride. The rate of this reaction is equal to the concentration of CHCl3 raised to the third power, and then also, actually, no, that is a typo. It's CHCl3. Okay, that's what that should be. That's just raised to the first power, right? So it's CHCl3 raised to the first power, and then Cl2 raised to the 1/2 power. So looking at this, I have CHCl3 is first order, Cl2 is 1/2 order, so I add the exponents. And so adding my exponents, I get 1 plus 1/2, which equals 3/2, right? So that reaction is 3/2 order, or the overall reaction is 3/2, as it's first order in respect to CHCl3 and it's half order in respect to Cl2. So the second question says, in this first reaction, what is the rate constant units? Right? So what are the rates constant units for that? And so when we look at our units of our rate constant, right? So B, we're going to say units of rate are going to be equal to the units of my rate constant times my units of concentration, right? And so for my rate law, right, what are my units of my rate going to be? Well, the units of the rate, right, are going to be equal to, right, this is a first order reaction. So my units of my rate are going to be molarity per second. So that's my units of my rate. So my units of K is going to be equal to my units of rate divided by my units of concentration. Okay? So my rate units divided by my concentration units. Right? Well, let's look at that a little bit. So what are my units for rate? Well, we said my units for rate, right, we're going to be equal to molarity per second. And my units for concentration, right, well, since it's a first order reaction, right, the units for concentration were simply molarity, right? So I have molarity per second divided by molarity. So my rate unit, right, my rate constant units is just seconds to the minus 1, right, which is the same as writing 1 over second. So my rate constant units are going to be seconds to the minus 1, and that equals 1 over second. And so the rate constant units do depend on the order of the reaction. So a first order reaction is going to have different rate units than, say, a second order reaction. All right? Okay, so let's do one more in this, and we're going to look at determining a rate law from initial rate data. Okay, so we have a data on a chemical reaction, and this is just a generic equation of A plus B going to form C. And so we have concentrations of A, and we have different concentrations of B, so we change the concentration of A, see how that affects the rate, change the concentration of B, and see how that affects the rate. So we're asked to determine first the rate law for this reaction, second, the rate constant, and then what is the rate when we have those specific concentrations. Okay, so we know that if we wanted to generically write the reaction, right, so looking at A, our rate takes on the generic form of K times the concentration of A raised to some power M times the concentration of B raised to some power N. Right? So looking at that, we can compare and see what happens. Right? So we can say, okay, let's look at which two different conditions do we want to look at. We want to look at the conditions where we're doubling A. Right? So we want to look at experiment 1 and experiment 3. Right? Because in experiment 1, we're keeping B the same, and we're simply doubling the amount of A. Right? And so looking at that, we can say, okay, so that means rate of experiment 1 over the rate of experiment 3. So we're looking at those two relative rates, right? And so that equals K times the concentration of A1 raised to the M times the concentration of B1 raised to the N divided by K times the concentration of A3 raised to the M divided by the concentration of B1 raised to the N, right? And so when we look at that, we can say, okay, well, our K is going to be the same. B1 to the N is the same. And so we end up with rate 1 is 4.0 times 10 to the negative 5 divided by 16.0 times 10 to the negative 5, right? And so that gets us, right, looking at those rates, right, we can say, well, 16, and then we get A1 to the m divided by A3 to the m, right? So this gives us, right, if we continue on with this problem, right, we can say then that, well, that means 1 over 4, right, equals 1 over, because I've doubled A, so that means the concentration of A3 compared to A1 is twice, so 1/4 equals 1 over 2 raised to the power of m, right? So what value of m would make it so that 1 over 2 to the m is equal to 1/4, and that would be if m equals 2, right? 1 over 2 squared would be equal to 1/4. So this reaction then says that the rate equals K times the concentration of A squared times B to the N, right? Well, now I've got to figure out what that N is, right? So when I look at the value to find out what N is, right, if I go back to my original data table, right, and I want to do that same thing, but now I want to figure out what is N. So I'm going to use very similar type of equation, and I'm going to insert my values, right, and say, okay, well, what we start off with, right, is if we look at B, right, and so we're looking at the concentration of B, so we're saying that rate 1 over rate 2 is equal to K times the concentration of A1 raised to the 2, because we know M is 2 now, so we can say, and then that's B1 to the N equals K times the concentration of A2 squared times the concentration of B2 to the N, right? Well, A2 is equal to A1, right? Because we didn't change the concentration of A from experiment 1 to experiment 2. So rate 1, 4.0 times 10 to the negative 5th divided by 4.0 times 10 to the negative 5th equals B1 to the N over B2 to the N, right? And so if we plug in the values for B2, then we say that that means that B1.2, right, because that was my B1. My B1 was 1.00 to the N over 0.2 to the N, and that's going to equal 1, because 4 times 10 to the 5th divided by 4 times 10 to the 5th equals 1. And so the only possible way for this equation to equal 1, right, would be if n equals 0, right? Because anything to the 0 power is 1. So 0.1 to the 0 divided by 0.2 to the 0 gives me 1 over 1. So 1 over 1 equals 1. Right? So that means that this reaction is 0 order with respect to B. So if it's 0 order with respect to B, right, then my overall rate is equal to K times the concentration of A squared times the concentration of B to the 0, right? And then we can just simplify that and say that it's K times the concentration of A squared. Okay, so that would be my rate law for that experiment, right, that we've calculated from our initial rate law data. Okay. Part B of that says the rate constant, right? What's the value of the rate constant? Well, in order to determine the value of the rate constant, right, we could say, well, we've got some data for this experiment, right? And we could say, well, we know the concentration of A, we know the rate, right? We know what the exponent on A is. And so we could solve for what our K is, right? So if we say that rate equals K times the concentration of A squared, right, then just rewrite that solving for K, and K is going to be equal to the rate divided by the concentration of A squared, right? And so if we take, for example, the first experiment, I had a rate equal to 4.0 times 10 to the negative fifth molar per second. And if I divide that by my concentration of A, 0.100 squared, right, then I've got 4.0 times 10 to the negative fifth molar per second divided by 0.1 molar squared, right? So K, 4 times 10 to the negative fifth molar per second, right, divided by 0.1 squared is going to be 0.01 molar squared. So that equals 4 times 10 to the negative third molar to the minus 1 seconds to the minus 1, right? Because molarity divided by molarity squared gives me a molarity to the minus 1, right? So that's my value of K. 4.0 times 10 to the negative third molarity to the minus 1 seconds to the minus 1, right? And again, that's because that's a second order reaction, right? Different units of K depending on the order of the reaction. Now, lastly, they want us to figure out what is the rate of the reaction when A equals 0.05 and B equals 0.1, right? Well, for this, then we would just plug in the values that we got, right, that we were given into our rate law, right? And so we've got our rate law. And so we know, again, right, part C, rate equals K times the concentration of A squared times the concentration of B to the 0. So if I plug in values for that, right, rate is going to be equal to K times my concentration of A, right, of 0.05 squared times my concentration of B, 0.1 to the 0, right? And again, K, right, K we determined. So this is going to be 4.0 times 10 to the negative third molarity to the minus 1 seconds to the minus 1 times my concentration, 0.05 squared, 0.050 molar squared, and 0.1 to the 0 is just times 1, right? So I end up with a rate, multiply this out, and I get 1.0 times 10 to the negative fifth, right, molar per second, right? So that would be my rate of my reaction, right? All right. So that is the first set of practice problems. If you have any questions, you can put them down in the comments or send me an email, and I'll try and get back to you as soon as I can. Great. Thanks.